Ricardo Javier. Am I pronouncing your name right? Rademacher?
Sure, why not? Yeah, it's all good.
And is your last name Minya?
So in Chile, we use our father as our last name, so that's Rademacher, and we keep our mother's name as our last name, and that would be Mena.
Oh, that's beautiful. Rademacher Mena. Ricardo Javier Rademacher Mena. Thank you for being here.
Thank you.
So tell
So yeah, let me know. Yeah, how do we want to do this?
Well, normally I can click to the next slide, but I think you'll get to do that because the PowerPoint's on your side of the computer. So you can.
So how I organize this is just a little bit of science, a little bit of art, and trek through that, and then eventually get to my thing. So this is kind of like a conventional PowerPoint, but with as few words as possible and as many pictures as possible.
Awesome. Sounds great.
And so eventually we'll build up to my pictures and my things, but at the same time I hope to show you that, like the title shows, how science and art are reuniting, and not just in not just in an ephemeral, but in a real visceral and practical level. That they may have never been separate, but now we're recognizing their utility in each camp.
Excellent.
Okay, so I'm just going to dive right in, and whenever anybody wants to interrupt or get further clarification, we'll just interrupt me there.
Okay.
So here we are. This is kind of how I have things organized, and about anywhere from 5 to 10 minutes in each section. And like I said, I want to front load it with talking a little bit about physics and math and music, because these are the things that I do. And then these are my my websites, because as a Sciartist, scientist and artist, that's how I express myself. Okay, it's not really about my journals, and it's not really about Canvas. For me, the website really gives me, that's my canvas, so to speak. And then, yeah, my current kind of thing right here with VA. Are we tracking good? Everybody can see? Everybody can hear?
I can definitely see, and I can definitely hear. And if anybody out there has any questions or problems, just type it in the chat box, and I'll check it. So, Ricardo, you don't have to worry about the chat box. I'll check it.
Perfect. Perfect. Teamwork, ho. Excellent. Okay, so, yeah, my name's Ricardo. I have a PhD of physics from the University of Cincinnati. I then created an educational game design company in 2005. And here at the Art Institute, I teach physics, game design, and physics of game design. Right now, I'm actually in my classroom, my physics classroom for Brown and Mackey, which is another school under our parent company of EDMC. And so I'm kind of doing presentation, a 2-for-1 presentation here, kind of showing physics and science everywhere. But then I'm sorry, go ahead.
That's excellent. I think that's smart. I think it's something that we forget to do, but we can definitely use one project for more than one thing, so we can save our time.
Absolutely.
Yeah.
Absolutely. And that's the Sciartist philosophy that I follow, is just reuse, repackage, reimagine things in different contexts, and you'll often get a lot of play out of that. So, and what started this right here is I started playing the bass guitar, about 3 years ago, and music theory and Lego for life. Just, since day one, 75, 76, 77, Legos have just always been there. And that'll become relevant as we track through this. So the first thing we're going to do is we're going to talk a little bit about physics, about the visuals that I like in physics and kind of that excite me there. And this is my choice for particle physics. And so particle physics is our, basic constituents of matter and quarks and electrons and all that. And you know, this thing is fantastic because this chart just chock full of information, organized, and this is going to become a recurrent theme, organized two-dimensionally, okay, not just one-dimensionally. And there's definitely an aesthetic, as any artist would recognize, the layout, the way things are organized, they're drawing the eye towards certain things, etc. So, you know, this is an infographic about our universe, about our particles, and it's a striking visual that at the same time inspires and educates. And then a very basic kind of infographic stuff. Oh, that's the wrong one.
I love it.
And this is just a sample for solid state. And solid state is one level up from particle physics. It's what the particles make, your atoms and your molecules and whatnot. And in solid state, there's a lot of talk about band gaps because that determines conduction and superconductors and transistors, and our computers that we're looking at right here really depend on all these figures and all these visuals. And, you know, especially this kind of thing where we want to see, let me see if I can get my pen going, yeah, where we kind of see a hexagon here, up there, and then another one here, or this kind of structure. And that's important, that's relevant. You know, these are also atoms right here. And that structure, that aesthetic, that proportion, that proportionality, all these things are relevant, very, very relevant to the science, to, sorry, a little bit bigger view than intended. Okay. Relevant to the science, symmetry, you know, I mean, what we call art, and by the way, I'm restricting art to visual 2D media. It still applies to sculpture. We can kind of extend it to dance, but when I say art, I'm really, you know, kind of speaking of the visual media, as it were. And so yeah, here just very relevant, very, very striking. This is quantum mechanics. These are the modern view of what the electrons look like. And on the right-hand side is, you know, kind of a mathematical sliced view of these waves and whatnot. But then on the left-hand side, we get a more three-dimensional view. And these are our atoms, and these are electrons. Okay, this is what, in principle, the best that they look like, even though we're looking at concepts like probability. Okay, so we're looking at thin air, but a thin air that has shape. And then if you've ever had chemistry, you might remember the sp, the f orbitals from the periodic table. And this is kind of how these two concepts line up and how these two shapes line up. So this is quantum mechanics. This is physics, and it already has a visual paradigm that's important. Okay, these shapes are important, the symmetries are important, and I maintain that you can be a great scientist, but if you don't have that aesthetic, that appreciation of proportion and how things fit together, that, you know, perhaps don't come naturally to an artist, but are certainly their forte or what have you, you're not going to be doing complete science. You're going to be doing half of it. You're not really going to be appreciating the whole thing. So this is quantum mechanics. Anybody that's ever seen quantum mechanics knows there's weird stuff going on here. No less weird than relativity, than wave-particle duality. So if you ever had a class, you know, on physics, you know, the light, is it a particle, is it a wave? You know, is an electron a particle or wave? Are you and I particles or waves? And this is a very real thing. You know, this cartoon kind of makes it a neurotic Woody Allen of it, if you will.
I love it. That's hilarious.
But that's real. I mean, in a sense that's the identity crisis that every single one of the particles has in our physics, you know. And relativity, you know, talk about weird again. This is the area of wormholes, you know, light cones. Okay, you are here, here's the future, here's the past, and this is like never, never land. That can be anything and nothing at all. And then, how many people saw Interstellar, the movie?
I haven't seen that.
Any positives on the shadow-sphere?
Not yet.
Okay, so in Interstellar, the movie, they're going around a black hole. Okay, this big black splotch is a black hole, and they have to figure out how to visualize it. Okay, the movie people. So the movie people turned to the physics people, and the physics people turned to the computer people, and the computer people made simulations, and they came up with this, which then the artists helped refine, and you came up with the final model. And as it turned out, both sides claimed they could not have done it without the other. If it weren't for the artists, the movie directors, and the cinematographers kind of looking at it this way, asking for asking the right questions, the physicists would never have thought to look at things this way, and now we have a more complete view of what black holes interaction actually occurs. And it's a critical part of the movie Interstellar, and a striking visual if you ever see it.
And one of the attendees did just chat in and say that it was a great movie. So one of our attendees has seen Interstellar.
Okay, no, great, fantastic. Yeah, so they know what I'm talking about with just how striking the visuals were in that movie. And let me build on that. That those were as scientifically tight as we could make them, and still give good science fiction. You know, like the way the wormhole was visualized, the way the black hole was visualized, everything really strove. The way no spoilers, but we'll leave it at there. Just everything was very well visualized. And I found this one, which I found really nice, because I like simple line diagrams, as you'll see much later on. But this is a beautiful summary of what relativity is, and general relativity, and special, etc., and all that. And this is really cool, because it kind of breaks down the concepts that physicists think in. We think space-time, energy, matter, and kind of not just one yin-yang, but actually two forming up. And yeah, so this is visuals help us put through concepts that words and math can't. I mean, that's why pictures exist. There's things we can do with words, and there's things we can do with pictures, and these concepts, abstractions, are really the forte of a visual medium. So this is a side note. This is one of my projects from many years ago, and that was to teach physics through a virtual world. So all of these environments that you see are three-dimensional virtual worlds in which our students would log in and take on the persona of a person. Then that person, and if you've ever played a role-playing game or World of Warcraft or something like that, about quests. You go up to a person, you ask them a question, hey, I'm looking for this, then they give you a quest, and you complete it. And in my game, that quest was more or less a Q&A. More or less, they gave you a question, and you answered, and it was either about physics or about the game or what have you, but that was the narrative that moved it along. And then it also had a more technical component where you would actually measure physics variables. So here you can clearly see the parabolas that 2D motion makes in gravity. Here's up and down motion, so we can replicate a physics classroom in 3 dimensions. And that project, I pursued it for a number of years, but then they're very expensive to keep up. And 2008, the economic bubble burst, the housing bubble, and just all kind of things kind of meshed together, and we put the project on hiatus. But this is an example of science and art, in particular the video games. Here I'm taking a video game paradigm, an education, an entertainment paradigm, and applying it for educational purposes, for scientific purposes, no less. Because I view this, this kind of idea where you go around the world and experiment with the world. That was a fundamental paradigm of the game and what I feel, people could take away from the game. So this is just one example of something that I did a long time ago. It doesn't have anything to do really with the end game I'm going to show you, but it fits the bill in terms of physics. Physics and music have a strong connection. This is Helmholtz. I don't know visual arts. I don't know if Ludwig Naus is anybody. Is a somebody? Is a nobody? Is a somebody?
Somebody.
Ludwig Naus. I don't know if he's a somebody or not, but he did that portrait of Helmholtz, and he's a physicist, just like I was, and he was very interested in music, and he gave one of the first physics accounts. And, I bring this up. I think it's a really interesting quote. Music stands in a much closer connection with pure sensation than any other of the arts. And, if we have any other artists here, including musicians, what do you think about that quote?
We could wait a minute while people type in, but if you don't mind, I'd like to say what I think about that quote.
By all means.
As an artist and as a musician wannabe, I just started piano lessons. I love that quote. I'm curious about it in a couple ways, but the main thing I'm curious about is how music is invisible, like the sound is invisible. And I wonder...
There you go.
What do you think? Is that why it's maybe closer with pure sensation?
I think that certainly lends easier to the spiritual, to the ephemeral, to that ecstatic, to that thing than a piece of visual art which is there, which in principle you can touch. As you say, music is invisible. And I think I interpret it in that context that music, you can close your eyes.
Right.
You can shut off, you can be thinking nothing, you can be completely locked out, and if you hear music, you are still connected. You're still like it's like immediate. And with the eyes, there's a lot more scanning. You kind of have to scan the canvas, get the sensation, maybe walk around the statue, jump up and down to get a sense of it. Art doesn't give itself at once, where music always gives itself at once. It's a constant stream of that oneness. So, yeah, I think that invisible definitely touches more that spiritual side of things, for sure.
And then one of the attendees has said, not sure about agreeing with the quote. I'm paraphrasing. Music can be more immediate. It's time-based, so it is different than visual art. That's interesting. So,
absolutely.
Time-based.
Absolutely. Yeah. If I were and I do take that a step further, I very much put music in the time spectrum as a physicist, and art very much in the space spectrum. When I see a clock, I hear it ticking. When I see a clock, I hear it ticking. When I hear a clock ticking, I see the clock. Right? I mean, it's like in each case, I can make, these are both sensations. I can kind of like internalize them. But with the music, it is a constant stream. It stops. Art never stops. The painting, the statue remains. It's more infinite. So yeah, absolutely. I mean, this is not a right or wrong question. And that's one of the things of the arts, and that's one of the things of music that motivates me. Is I'm motivated not by sensation, not by right or wrong, but by really psychoacoustics. Okay, I want to say, look, your view, what the attendee just expressed is absolutely valid. What I said is absolutely valid, and other opinions are absolutely valid because these are our sensations. But we all have to agree on the physics. And we all have to agree on how sound comes in and some basic paradigms like frequency and time. And this is foundational for me. So when I studied music and when I went into music theory, I tried to get to the heart of it. And the heart for me was psychophysics, psychoacoustics. And these are two Absolutely fantastic books. They are advanced, but for anybody that teaches at the college level, like our audience, these are totally addressable, accessible, you know, and they're just fun reads. Especially this guy. This guy's just really got good graphs and talks a lot about music. So if you're interested in music on a grossly physical level, check out one of these books. Check out Psychoacoustics. It's really interesting stuff.
That looks good.
Now, go ahead, sorry.
It looks good. Thank you for those 2 book suggestions.
Yes, yeah, and you know, I'm sure the PDF, you know, is accessible. So all these things are large format images in the PDF. So if you want to rip them from there, and of course there's the link underneath. This isn't strictly physics. These is, if you're not familiar with it, the National Science Foundation VISI Awards, the Visualization Awards, given every year for I think like the past decade or so. And so this is the 2016 winners, this is 2015, 14, and this is 2013 winners in each column. And these are awarded for the expert and People's Choice awards for the best visualizations in science. And what you can see is this is a combination of both abstract, you know, like these guys, abstract in the sense they're not infographics, they're not, well, basically exactly that, they're not infographics, and then the infographics, you know, these guys. And yeah, I'll just, you know, they're just fantastic. This one, for example, is an artist who did a rendition of neurons, the neural tree, and so it's kind of like a forest tree paradigm, but it's also a black and white kind of yin-yang growing into each other, the black lines into white, the white branches into black, and really striking, really striking. Then we have supercomputers and physics, bubbles, modeling bubbles. And this is all about the beauty and simplicity and complexity of the physics behind these suckers. These are every child's plaything, every dog chases them, etc. And yet, to be honest, physics and math don't really have as firm a hold on them as we'd like. You know, so that motivates this infographic. This is turbulence flow around coral reefs. So that's water. Those are water streams. That's a top-down view of I don't know how many tens or hundreds of miles along the coral reef, and then imaged and visualized through it. And yeah, so on and on. So even the National Science Foundation supports the arts so strongly that they give an award each year strictly for that concept. And they're actually not only ones. How many people are familiar with CERN, the super collider in Europe?
We'll give people a time to chat, but I have to confess I'm not.
You've heard LHC, the Large Hadron Collider, that kind of business.
I think one of our attendees is familiar with it, but you know, I'm not. I'm embarrassed to say.
No, by no means. This is a huge super collider where they just run particles around and around. So if we were to look top down, it would be like, you know, like maybe I think it's a 2-mile radius ring around town. And this is what's inside. This is like the tubing. It just runs around it. And then actually these are the detectors. And what happens is they run the particles at the speed of light round and round and round and round and round and round. And then eventually they collide, like right there, and spew forth particles everywhere, which is exactly what we see in the lower right-hand corner. Those are particle tracks, and that represents the actual experiment. Yeah, no, those have been, yeah, very much in the art scope, as it were, you know, very artistically motivated for many, and it's necessary because green and red and purple and blue, they mean something, right? And not only that, but straight versus curved means something. And this is this is beyond physics. This is art. This is aesthetic. This is pattern recognition.
Yeah.
And we have supercomputers doing it, petra, tera, exabytes of data flowing through it, but we still have projects like where we crowdsource it because the human eye is still infinitely better at parsing through this data than our algorithms. And, oh, by the way, just if you hadn't noticed, that's a person. Yeah. So if you ever watch any anime and you see some of their fantastical things, you can be sure they're getting their inspiration from these kind of science installations. And before we leave this, they have a specific site, arts.cern, where they hold a contest each year to bring an artist. And this year, the winner is a South Korean composer called Juma, J-U-M-A. And I don't remember, I don't know exactly, but I think he's going to be like pouring liquids down here and touching them with something and making music.
Whoa!
Yeah. Yeah.
I want to do that.
Yeah, no, I was thinking of applying, but I just couldn't get my focus because I just, I felt like I was a lantern with a lot of ideas, but I wasn't like laser beam focused, so I couldn't really, give, like I had a billion ideas of what they wanted. But it's crazy, yeah, musicians, artists, dancers, basically the contest says, we want a collaboration between artists and the physicists at CERN.
Wow.
It's not just kind of like a long-distance love affair. It's very much you go there for a month, you live, play, work with these people, and they with you, and the result is an organic collaboration between the two.
That's exciting.
And every year, it happens every year, and especially for our students, I think these are the kind of things that anybody can do online or offline, that anybody can apply for. And if you have a class that wants to kind of like just self-organize around it, kind of work around it or just follow it, I think it's, really cool to have these non-conventional outlets for art. Because I've flowed a little bit around in the art kind of pitching world, and, it's nice to have unconventional places.
Yes.
So this is a personal side note where in 2001 I attended the opening of the Michigan Center for Theoretical Particle Physics. They called their thing the 2001 Space-Time Odyssey. And as part of the exhibition, 10 works were commissioned. And each person was given $1,000 to make an artwork based on physics. So it was a art person and a physics person from the Michigan working together. And this is one of the artworks, which is actually a weaving.
Oh.
It's actually a weaving. It's not a painting.
Oh, that's great.
And it represents those tracks that we saw. You can kind of see them lightly kind of emblazed. You can kind of see it there. Yeah? See, what they're showing here is normally a quiescent detector with no tracks would be this color right here. I don't know if you can see my hand. Can you see my hand?
Yes.
Okay, so it would be this color here, and these dark colors are tracks where they recorded hits. So if you follow the dark spots, you can kind of see the tracks where they kind of like the particle goes out. And in any case, the dark is where particles are, the light is where they're not, and this is a weaving. They, he, she, they, I don't know whom, they collaborated and made this, and this same team did this other weaving, or quilt. I don't know I think it's a quilt, perhaps would be a better term. And this is called Bubble Chamber, and it's again a replication inspired by the particle tracks that are part and parcel of our particle physics.
Beautiful.
So yeah, and I had the pleasure of attending there, and I got to meet Professor Higgs of the Higgs boson fame, and several other physics luminaries. So it was like like a geek event for me, for sure. But it was 15 years ago, and to this from that day, no matter what I've been doing, I've always carried that art, that little factoid that they actually made art a part of the inauguration. You know, like the opening part, like it was an integral part of that. And there's installations around, etc. And on another personal note, another reason why this is so interesting and relevant and coincidental is because I'm from Chile, South America, and I don't know if you're familiar with Violeta Parra or the Arpilleras, and she was a socialist, hippie, artist. She was a weaver, a farmer, a singer, a writer. She did it all.
Wow.
She communes in the country, and her artistic claim to fame internationally are the arbellas, which are woven portraits, woven artwork. So all that is woven. I think crochet might be. I don't know what crochet is, but here's another photo taken by somebody else, which kind of shows you, I think, the three-dimensionality of it. You can see how it's the sheet.
Yes, and the texture. I can really see the texture.
Good. Yes, exactly. Because I went to the museum, and boy, howdy. I mean, it is artwork that you have to see from every angle. I mean, you got to get light. I mean, yes, exactly. Because it's like it's 2.5 dimensional. You know, it's not quite 3-dimensional, but that texture is very visceral. Like down here, the way that baby is on top of the mother, quilted on top of the mother, and you can just see that 3-dimensionality. Now, she used her quilts for political purposes.
Yes.
So her quilts were very much a statement against the political regimes of the time, and you can kind of see,
yes,
you know, very, very dark model down here of God knows what's going on, but devils and hangings and things like that. But throughout it all, she always kept singing in poetry and such, and there was a fantastic movie made about her, and her force of character came through when her daughter said, and I'm paraphrasing, but her daughter said, you know, I wish I was dead. She was just livid and just like in the conditions. I wish I was dead, the daughter says. To which the mother, Violeta, comes over and slaps her soundly on the cheek. And she says, daughter, you either do or you don't. You don't talk about that. And sure enough, I mean, she died of suicide, just a self-inflicted gunshot wound. I don't remember how old she was, but you know, I don't think she was 50. Okay, so in 40s or such. So she was, you know, she was a woman of strong character, of conviction, but she was the first, and I think I've got this right, she was the first textile displayed at the Louvre.
And what is her full name? Violeta?
Parra, right there.
I can't see it because my go-to thing.
Oh,
How do you spell it?
Oh, hello.
Okay.
It's VOA. There you go. Can you see it now?
I actually can't, and one of the attendees is curious about it, and I think that person might be on the phone.
No problem. It's
okay.
a P-A-R-R-A. Violeta, V-I-O-L-E-T-A.
Gotcha.
Parra.
Got it.
Yeah.
Thank you so much.
Yeah. Yeah, no, she's great story. There's a movie. Mm-hmm.
Okay. Violeta Parra.
Yeah, not like Bob Dylan or anything, but she's more
maybe more real than Bob Dylan. No, I'm just digressing there, but go on.
Yeah, no, just more active. I don't know my 60s musical revolutionaries or anything, but more Woody Guthrie maybe. I don't know. I'm just throwing it out.
Yeah.
Yeah, I think that's more it. I mean, if Woody Guthrie had been unstable and killed himself, I mean, she was,
wow,
by all accounts, unstable and just throughout her whole life. So yeah. So yeah. So now let's go a little bit into math, and these sections are a little bit quicker because in terms of the math, you know, when you think of visuals, I think of Legos, and we're really kind of pushing, not the envelope, so to speak, but there's really more attention to visual and math, okay? Because of visualization, because of data mining, we're really paying a lot more attention to that. For example, this is one of my books that I really love called Visual Group Theory. And these are groups. These are actually mathematical diagrams. They are math in every sense of the word, but they have shape. There's something. Like this is like a buckyball, if you've ever seen that. But that's a math thing. It's not a molecule. It's like the math behind it. And this is a cube, but it's also a mathematical structure. So we're definitely probing. We're definitely looking at math a lot more visually. And you'll see later on why these diagrams really speak to me. And I wanted to draw your attention to one thing called set theory, which is like what we know as math. These are its symbols. Okay, they give me a headache. I'm not, you know, I'm a physicist. You know, what was it from Star Trek? Damn it, Jim, I'm a physicist, not a mathematician. I mean, that's true. This is really, really harsh, and you've got all the, you know, and this is a proof. This is, and here's the thing. This is normally what a proof looks like.
A proof.
Either absurd or not.
Interesting.
But there's a new math on the block called category theory, in which the proofs look like this.
Ah.
So yeah, right.
Yeah.
A little bit. Go ahead.
More accessible.
More two-dimensional, right?
Well, now that you mention it.
Here's the hidden thing that they never tell you, right? These proofs, this is one dimension. This is one dimension. This is one dimension. You go from top to bottom and you read the proof that way. Unlike art, which is like you can look down here and then look up here and then put it, you know, you make it. No, you have a start, you have a finish. That is one-dimensional thinking. That is one-dimensional proof. Category theory, boom, uses two, and it could even be argued could benefit from a third dimension. But this is proof. This is math. This isn't three dimensions. Okay, this is not three dimensions. Not 3D. Okay, this is just an abstract figure. But if we put it 3D, we humans can parse it, can feel it, can manipulate it much better. That's math. That is category theory. That is a new math on the block. I'm very excited about it. And like I say, these diagrams very much take the place of these headaches. So art is coming in a big way. And by art, I want to specify this is graph theory. This is network theory. So we already kind of have a name for the art that we're using, if you want, the art theory. And it has its own rules and its own nuances, etc. But I love it. I can't get enough of it. I can't evangelize enough. Category theory, look out for it. It's going to hit the charts, #1, before soon. Invest in it. If you want to buy stock in it, watch out.
I'm just going to make a little note in the chat box about category theory. I love it.
Absolutely. So here we are in another side note before we dive into music, which is my main thrust, my main thing, and that is Escher, MC Escher. As artists, I think most of us, visual artists, I think most are familiar with the work of MC Escher, or at least have seen their, you know, these infinite staircases that are visually impossible if you really are physically impossible. And what few people know is that he had a very close collaboration with mathematicians like Roger Penrose and Co. Exter. These are luminaries in the field, and they corresponded back and forth, and they helped each other. So this titillation, called a periodic tessellation, angels and demons. Can everybody see the angels and demons in there?
I can. I hope everyone else can. It's beautiful. Weird and beautiful.
And that's math. That's a hyperbolic plane. That's a mathematical construct that shows you this is an infinite surface of these guys, and this is what they look like to us. It's like if we were to flatten out a sphere and we make a map, and it comes with all kind of weird distortions. Well, this is the same idea, but with weird spheres and weird maps. And this is Escher, and he talked with Coaxer, he talked with a mathematician about these things, and you know, they learn from each other. So the connection is real and visceral. And this is just one example. If you look at Picasso and Riemann, and you look at some of the other cubists and surrealists of the early 1900s, they were in bed, perhaps even literally, with the mathematicians. So, you know, and scientists of the time. So there's a very fertile pollination, to continue the pun, in that field.
Yep. And one of the attendees just said how I feel, which is, look, just, God, that's awesome. That really is awesome.
It's there. It's always been there. You know, it's like it's not hidden from us, so to speak, right? Yeah, it's always been there. We just don't emphasize it. I think the scientists are guilty of not emphasizing the arts, and the arts are guilty of not emphasizing the science.
That's right.
And so we both have to build our bridges from each end. We can't expect the other one to build the entire bridge by themselves, because they can't, you know. So that's the nature of this discovery, is you just mine the internet and it's already there. I mean, look at this topic. This is visual music. You know, nothing could be more oxymoronic than that. Visual music. And yet when you think about it, well, absolutely, you know, there's absolutely visual music. I mean, the very nature of staff notation and lead sheets, you know, it is visual. It requires a visual acuity. It requires hand-eye coordination, to be sure, but it's a language. It's an aesthetic. You can absolutely start seeing little patterns in there that are relevant. Yeah? So it has that. But, again, it's just one-dimensional. This code. Okay? So again, it looks like we're talking about a two-dimensional picture, but it's actually a one-dimensional snake. You start at the beginning and you end at the end. Okay? So again, if we adopt this viewpoint, we have to start seeing science as one-dimensional thinking and then two-dimensional thinking. Now, this is conventional thinking. This is unconventional thinking. So this is taking liberties with staff notation, making your own system, what have you. I think this fellow made a peace sign, just kind of cut and pasting. This is a very humorous.
Oh, I see.
For anybody who's into music, I mean, it's just hilarious. And, you know, let me just fast forward right there, yeah. Right there at the very end where it says, at a time signature of 2/32. So it covers all the annoying bases. It's really, and this is, I think, an ode to, like, Gregorian chants, maybe, you know? It's got that duus, that Gregorian kind of look to it. So there's conventional, there's unconventional. Oh, no, come back to me. There we go. And then another conventional one for music is called a clock notation, and that's where we put our notes around, and this guy at the top is chromatic. So these are 1/2 step. This is 1/2 step, 1 hour, 1/2 step, 1 hour, 1/2 step, 1 hour. And that's a clock. We call this the chromatic clock. But we can also do 7 half steps and move in perfect fifths.
Sorry.
Yeah, it's all about it. I say, you know, I get that all the time when I say perfect fifth. Wait for it. No. I thought it was like Candyman. Like say perfect fifth, perfect fifth, perfect fifth. And this is it. This is very famous in music, the chromatic circle and the circle of fifth. And then this is my version of it. I'm not going to go too much into it, but it's a spiral diagram where I've kind of adopted it, and I created a mathematical equation that goes along with this and goes along with these other visuals. And this is just my personal attempts at understanding it. It doesn't have to be original, doesn't have to be new, but it's my way of looking at it, and it kind of starts rearranging my neurons, my brain to accept information. You know, it's not making this invalid. It doesn't make this invalid. It just kind of, you know, puts both of those together into something that makes sense to me. And yeah, so before we go into some of my works for the final segment, these are some of the other visualizations you can expect in music. In the upper left-hand corner, this is equalizer-based music, which is basically spikes and peaks are going to move, and these things are going to wobble based on how much bass there's in or the melody or what have you. Of course, you've got your laser shows, you know, just doing all kinds of crazy things. Projections are very big, where you've got your DJ in the middle and you just project on top of them. And then I'm a particular fan of Plastic Man, and in the lower right-hand corner, he's an electronic DJ. He created this monstrosity. Okay, he's inside of it.
God.
And you can see the crowd to get the scale of it. It is humongous, and it's entirely projective. So I think it's a pyramid, or it's either a pyramid or a rectangle kind of cylinder. And yeah, so he's in there and doing all kinds of visuals with the lasers and whatever. And he premiered at the Guggenheim. You can actually probably download, if you go Plastic Man, plastic with a K, and Guggenheim, his performance might pop up.
I'll do it.
Okay, so in these final minutes, these are my works. These are my visualizations, and they all center around music. So what I did, and as you see there by the tagline, I kind of consider mine to be a modern music theory. And honestly, folks, I consider it to be the real music theory, because I'm starting from math. I'm not starting from feelings, nothing more than feelings. Whoa, 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 feelings, none of that. No subjective sensations like minor makes me happy, major makes me sad, or vice versa. None of that. I start from math. Sorry, go ahead.
That's interesting. That's very interesting.
Right? Yeah, because I'm Hispanic, so I have been blamed of being emotional, but I'm also a man, so I've also been blamed of being unemotional. So I can just I can put both of those in there. I can absolutely be unemotional about how I create this, and then be very emotional about what I've created, right? So I don't need emotion in this for it to be emotional for me, nice, so to speak. And yeah, so Key Chord Mode is my first website. Like I said, I write in websites really well right now. By the way, PowerPoint is a powerful research tool if you haven't used it. As you see in this presentation, if you can organize your thoughts one thought at a time, it's the real nice way to do research and think about things, or even produce art, because then you can iterate. I've had PowerPoints that are 50 slides long, because I start with an idea on slide 1, and then I copy. I never erase. I never modify. I just keep copying and keep copying, and then make version 2 when those copies get too much, and then keep going. So art tools are everywhere. I use Excel in the same fashion, just to kind of create this. So this was created using PowerPoint, these visuals. All right, all these squares and everything. These are all PowerPoint squares that I've used to create these pictures. And I'm not going to go too much into the theory, but for those in the know, what happens is that I can mathematically break up music into, these are perfect fifths and tritones. So the purples, any purple arrow is a perfect fifth, and that's a tritone. This is a major third, and this is a minor third. And this is a major second, that's a whole step. And this is a minor second, that's a half step. And that's that's the code, right? That's the legend. And from these arrows, I just take those set of 6 arrows and then map music. Okay? And again, if you're in the know, what these blocks are the modes of music, scales, that concept. They're composed of notes, but they're not necessarily notes themselves. And yeah, so by doing that, like I said, you get these diagrams. For example, this is my version of a 7-note scale, 1, 2, 3, 4, 5, 6, 7, across 12 keys. So this is how I view the 12 keys, by basically putting every scale in it.
That is cool. And I like the colors.
Yeah, so the colors here are a major third. So this represents from the start of an arrow to any other arrow. That's going to be a major third, 4 half steps. And then anywhere you see these black arrows, that's a tritone. That's going to be 6 half steps. And yeah, exactly. So, and then it just gives you that kind of visual where now you look at it, now these are notes. Now the way that these notes are organized within the scale are two-dimensional. This is not a one-dimensional construct anymore. You know, same thing with this little fella over here. This is the Ionian mode. If I were to put C, let me make it small because I don't think I can write. If I were to put C in there, then this is E, that's A, that's F, that's G, that's B, and that's D. And then you find out, well, this is a major third away from each other, that's a minor third away from each other. So you create these consistent diagrams. And honestly, you get crazy, I get crazy with the visuals. And that's why I created another website called Orijinkan, and that's a word that I made up. I've always been a fan of origami, and I kept on feeling, boy, what am I really studying when I'm doing music? And I don't know if it was you, Lucretia, or responding to somebody else, but you mentioned it early, and it's time. When we study music, we are studying time. And so these visuals and that paradigm and everything kind of made me think, well, we're folding time, not in the science fiction wormhole, but in the sense that tritones and octave equivalents and all these things fold these notes, fold time, so that we can create emotion. Yeah. And like I say on the left, Orijinkan derives from the Japanese. Ori means fold, and jikan means time. And so whereupon origami uses folding paper to create visual art, Orijinkan uses folding time to create oral art. So art for the ears versus art for the eyes.
Ricardo, that is beautiful. I love that.
Yeah, no, I like that. I had to, by the way, as soon as I figured it out, I just had to buy, as soon as I kind of came across that name, I just had to play into it. You know, just like, it plays nicely against the space version of origami. The paradigm is fertile, like as you'll see at the very end, I'm using it to expand, etc. And it's based off the math. This little diagram off to the over here, this is math. This is real. Everything down here is music. This is not me.
So pretty.
This is just, you know, 4 ways of summarizing the modes. And what I did is I found like this 6-arrow code that I then used to create even prettier diagrams. You know? And again, these are mathematical and musical. So this is not my aesthetic. This is not my choice. This is not my emotion. Right? I don't feel one way or another about this. This is just the way it has to be, following the rules of music and math. And that's what I search for. That's what I reach for. That notion that by being completely unemotional, completely unfeeling, you can achieve beauty.
That's an objective aesthetics, I would call that.
So, say again?
I would call that an objective aesthetics.
I completely agree with both words. Absolutely.
And
absolutely.
Also, it was one of the attendees who commented on the nature of time. So that, I want to give credit to the attendee. And then the other thing is that same attendee suggested or mentioned that there's an art show you might like I think, I'm not sure of the full name because I can't access the comment anymore, but there's an origami exhibition that one of
Oh, for sure. Okay.
that you might like. The attendee was just suggesting it to you, Ricardo, because you might like it.
That is, thank you for putting that on my radar. Yeah, I will absolutely seek that out. As I was saying, the Origin Con is my kind of subjective philosophy, what have you, but origami is very objective, and there's a lot of physics in there. There's a lot of physics in origami. And there's a gentleman who did a TED Talk who's an MIT physicist who has a fascinating backstory. Basically lived as a hippie with his parents, self-taught, went to MIT, and is breaking paradigms, and his gig is origami.
Ooh.
He's studying origami at MIT. Yeah, so that would be a good follow-through.
And I think
I can also make diagrams like this.
I think it's called
sorry, go ahead.
The fold. And also the attendee just said that MIT guy is in the exhibition above the fold.
There you go. Makes sense.
Awesome.
Makes total sense.
Awesome. I love this one. I know this one.
Yeah, this is the same idea as before where I'm locking everything together, but what I've done here to kind of show the power of the diagram is that in music theory we also have chord qualities, which means that if you play a triad or four notes next to each other, they have a certain quality to them. So there's a major quality, there's a minor quality, there's a half diminished, fully diminished, there's an augmented quality, and this is the dominant quality. Okay? And you'll recognize this. This is Ionian, this is Lydian, your Mixolydian, etc. But the point of this diagram is that this is across 3 different scales. So it's 21 modes, or 21 notes if you want to think of it that way. 3 scales, 7 notes per scale. And they organize this way. Again, no aesthetic. I mean, there's an aesthetic here, like you said, an objective aesthetic. And that's a great word because I am objectively organizing this so it's pretty.
Yeah.
Absolutely. I was searching for this. I know these are important in music. See, this is why music is important. If I did not have this musical background, this would be a mathematical structure and that's it. It wouldn't have a context. But because I know that the major and the dominant and the augmented are something different than these guys. Okay? So there's a strict line down here that separates it. And that's musical. That is not mathematical. We get that from our chord qualities. That's teaching me something. That's guiding me. That's telling me something not just about the music from whence this came, but also about the math that can be applied to other things. And yeah, so these kind of diagrams, this is the final version. This is the most complete diagram, very mathematical, very strong ties with category theory that I can make, very unified and symmetric. You know, it flows. And the way that I want you to think about this is I want you to think of this as 2 circles.
Ah, okay.
Yeah. And that thing of 2 circles comes up in music and the sciences all the time. And this is a bigger one where this one is 10 scale. So this is 70 modes in music. And I am claiming that this has never been before done in history where you put 70 different scales, 70 distinct modes, 70 distinct 7-note things in relation to each other. There's a lot of work in mathematical music, a lot of diagrams, but I'm claiming nobody has done this before. This big old mess, which is like a city map. I mean, it's not complicated, folks. You look at some of the mathematical music out there, and it's hideous. I can't even read it. But this I can teach you. You know, this eventually I can walk you through it because it's pretty, because it's colorful.
Yes.
Because you can make it your own.
Yes.
You can take as many of these as you want out, put as many as you want in, and it still works. So you don't have to accept my whole reality to make use of my reality. There's certain self-consistent things that make it real, but you can absolutely make this your own. And this is Kickstarter. I then transferred that ideology to not a 3-dimensional, but like a 2.5-dimensional thing, where now I'm encoding chords modes or keys, I'm encoding that into singular Lego sticks. And so this is the Moonlight Sonata. This is my version of the Moonlight Sonata by Beethoven, and starts in the key of C, then it goes to the key of D, and so on and so forth. And then I did a bunch more in jazz. Oop, no, back it up. Okay, we'll just move here. And these were the rewards that I was offering for the Kickstarter campaign. And it plays to my model. Each one of these individual sticks is a different mode consisting of 7 notes. And then each one of these stacks is that 3 key chord mode thing. 7 of these stacks make a cube. And so each one of these Lego pieces is a component, I want to say teaching, but that's really doing it a disservice. It's a tangible visual music. You can touch it, you can hear it, you can touch it, you can feel it, you can taste it, you can lick it. It's Legos, non-toxic, and it represents music. And so here we are. This is the end. And so right now, what I'm doing is I've got another website popping up called a V8 Universe, and where I'm trying to put all these separate ideas together. And I'm trying to kind of test run it, saying I really found some powerful things of math while doing my music exploration. Where could that lead me? Okay? It's not emotional. Remember, the music guided me, but there's no music in there. I mean, it can apply to anything else that has math. And so I've, given it a couple of test runs over the last couple of months, found some interesting things, and so now I'm creating another website where I'm exploring that paradigm, and I create pictures like this. These are kind of like this is my mathematical proof. See, maybe to my disservice, maybe this is wrong mathematically, we'll find out, but this is the way that I do my math. This is how I'm proving my the method, using diagrams like this, or diagrams like this. This is my version of the periodic table.
Oh my gosh.
Organized. Here's hydrogen. There's helium, lithium, beryllium, and there's strong patterns that flow through it. A very simple way that they're organized. If you look to it, essentially each one of these links with the ball, something in the middle, and then another ball. These guys have a numerical relationship. And it just tracks through it. So just mapping the periodic table like that, you get these very objective
aesthetics. Objective aesthetics.
Very objective. Where all I'm trying to maximize is synchronicity. It's like the same pattern, This pattern, this guy, is the same as down here. Different elements, but the same thing, you see? And I can make this into a billion figures, but the point is the similarities are always going to be there, right? So it doesn't matter how subjective I get with the figures. Here I'm drawing attention to the similarities which exist beyond my subjectivity, beyond my choices of diagram.
I wish you were my math teacher
so that's it.
in college. I really do. I think I would have done a lot better. And I think I would have enjoyed it. And if for some reason someone has to leave, like right now, a link will be sent to you for you to have your faculty development credit, given to you. And if you don't receive a link, just contact Hannah at hmiller@aii.edu. But before we go, Ricardo, tell me about this last page, and then also I have one more question before we go. The
periodic table?
Oh, also, one of the attendees said Legos equals beautiful.
Oh yeah, no, Legos are like I said, and let me see if I can, no, discard. Yeah, I mean, it's not just me, right? It's like other people absolutely
love Legos.
And I read, by the way, this site right here, Teachers, Top Teaching, Yada, using Lego Build Math Concepts, has a whole page filled with these really obvious right? Okay, sorry. Obvious if you're in the know. 2 by 2, 3 by 3, 4 by 4. You know, that's very obvious, but the way, when you look at it, when you play with Legos, when you feel it, when you touch it, when you lick it, when you step on it, it becomes real.
Wow. Gosh, I just wish I had learned math this way. I mean, seriously,
Well, you still
Ricardo,
can. It doesn't stop you.
looking at that last slide of yours and then comparing it to this Legos, my brain just opened. Like just that brief look at your periodic table through colors and numbers and then looking at the Legos, my brain completely just expanded open.
And that's because that's the fundamental, you know, that was one thread through this discussion, is that notion of one-dimensional thinking versus two-dimensional thinking. When you're one-dimensional thinking, what you're doing is you're like a train and you're trying to hold one thought and then get to the other and then get to the other and get to the other while holding this caboose together in your head.
Right.
Okay? When you have two-dimensional thinking, you build the caboose. You can build a little bit here. It's like building a jigsaw puzzle, right? You don't build a jigsaw puzzle from the upper end to the lower end in sequence. You build the puzzle, in essence, how you build a puzzle. Maybe you work the edges. Maybe you work the colors. Maybe you sort by any, you know? So that's the difference. I view teaching science, teaching math, researching it should be like a jigsaw puzzle, where the researcher, it has the opportunity to choose how to do it instead of just, okay, I have to start with A, then go to B, then go to C, rinse, wash, repeat, you know.
Mm-hmm. Excellent. Excellent. I have one last question for your last slide page. Are those the ways we can contact you?
Yeah, sure.
Excellent.
Yeah, you know, I've got my Art Institute address, personal address, LinkedIn, if you want to follow up on anything there, and then the websites that my websites that I discussed, right down there.
And then my last question is, and this won't even take long, I'm just wondering, how do you keep your arts practice going with a heavy teaching load? How is it that you make your art? And then the other part of that question is, how do you get it out there? How do you find the time and the motivation along with earning?
Well, I can answer the second one first, and that is I don't. I have no idea how to. Just flat honest. I build stuff because I have to, not because it needs to get out. And I just have no clue. I have no gift for it. Even during my entrepreneurial days, or because of my entrepreneurial days, I realized I have no gift for it. I don't.
Me neither.
So that's the second one. As far as the first one, again, you know, it's kind of like a flip side. It's I have a heavy online teaching load, so I can do my art.
I see.
Versus a heavy offline teaching load. Yeah.
I see.
Absolutely.
Okay. Okay.
Yeah, I started teaching online when I formed my company for that very same reason, where basically I could run my company and my teachings on my schedule and mix and match them. And as I got more proficient at it, taking more and more classes, more optimal, flowing through it, etc., then I can work that and then take on bigger and bigger projects and just kind of flow with it a lot smoother. If I was offline, there would be a lot more, not time restrictions. It's not that you're spending more or less time, but what's the word? Fixed points in time and space.
Right.
To quote Doctor Who.
That's perfect. That's exactly what it is. I totally know what you mean about that. Well, I love your art. I'm a fan, and I am so thrilled that you let me let it be the banner art for our social media. Because for those of you who might not know, we have AI has social media, and Ricardo's art has been featured a few times as the banner art, and I'm hoping that it will continue to be shown as the banner art, Ricardo, because I think it's incredible.
Thank you. Fantastic. Thank you so much.
Thank you for being here and for being the visiting artist.
All right. Yeah, and like I said, my email's always open. So If anybody wants any questions, follow-ups, curious about, I try to document as much as possible, but if you're still curious, just drop me a line.
And this is being recorded, and I think we're allowed to share it. So if you'd like a copy of the recording, just let me know. Well, I should put my...
I do. Yeah, I'm going to YouTube the heck out of this, so for sure.
Okay, cool. I'm just going to write in my email address. It's lucksmith@aii.edu. That's lucsmith@aii.edu. Ricardo, thank you so much. This has been just
Thank you.
a true pleasure.
For everything. Thanks for allowing me to speak about it, and thanks for the attendees for sticking through it.
Awesome. Okay. Bye, everyone.
Take care, everybody.
Take care.